Okay. I hope it is all right now. Okay, this is a computer is a formal system. This is a direct implication of the requirement that each step in the effective method is precisely predetermined. Well, this is formal system vis-a-vis what? Historically, actually the way things were developed, especially in logic, is that in the beginning people thought, oh, this sounds okay, all right, this is very fine. Later on, as it got sort of refined, people thought, no, we must, whatever proof you have or whatever logical deduction you say you have, you start with some, you have to start from some given truths, which are called axioms, all right? So this axiom in the this is all in the Greek time actually, when the Greece was in the top of their civilizational this thing. So they say, so what developed was an axiomatic system. That is, you start with some axioms which are given, and then from those axioms you derive whatever you want to derive or prove whatever you want to prove using sort of acceptable kind of logic. Next, the development came, so people thought that this, what is acceptable, this is very vague. Okay, so we must formalize that part also, that whatever deduction step you take, that must be sort of, that must follow from some given rules. That means whatever, I mean, so you start with the problem, let us say, so say the statement of the problem, and then you take different steps. So each time you go from one state to another, this transformation from this one step to another by taking one logical step, that also has to be defined somewhere. So that is when we came to formal systems. We will go into the details of formal systems presently. So we had insisted that the computation has to be, has to be an effective method. That means each step is precisely predetermined. All right. So we will talk about, and of course there are various, I mean many formal systems, and we will follow some specific formal systems for our purpose, so that we are trying to do this in a very formal way, logical and formal way, or mathematical way, if you like to put it that way. So what is theory of computation? It is the study about the ultimate capability of computers. Note the word ultimate. What do we mean by ultimate? Well, we have not produced the biggest computer which can ever be produced. We are all the time we are producing bigger and bigger computers. So what exactly do we mean by ultimate capability? So obviously, if you are talking about ultimate capability, we cannot refer to some specific machines which have already been, I mean, realized. Rather, we sort of try to do it mathematically, so that whatever computer or
Sir, sir, your voice is muted.
Sir, your voice is muted.
Hello, you are muted. Hello.
is it all right now? Is it
Yeah,
all right now?
yeah,
Yeah.
yeah, yeah.
Okay. Thank you. So theory of computation, as I was talking, is the is about the ultimate capability of computers. That means we have to do it formally, mathematically, rather than refer to some already realized machine. Okay, that is, what problems can be computed? Can every problem be computed? Well, no, the answer is no. So naturally, we would like to know what cannot be computed. And maybe in your flat course, you have already heard about the, let us say, the halting problem. It's a problem which cannot be solved. Okay. So we are going to go somewhat deeper in that. And what can only be solved partially? There are problems which can only be solved partially. We will get into that by any computer that
Sir, you got muted.
Hello.
Sir, you got muted again.
Sir, you are muted again. Hello. Hello, sir.
how did this happen? I do not know. I'm not an expert in this at all. Okay, I hope it is all right now.
Actually, in participants list, there is a mute all button.
Oh, participants can mute all. Then that is very sad.
Turn it off, I don't know.
Yeah. So please leave that mute all button aside. Okay. So it is the so as we are saying, the theory of computation, it is about the ultimate capability of computers. What can only be solved, what can be solved, what cannot be solved, what can only be solved partially. Okay, under the limitation of being physically realizable and employing only effective methods. Okay, these are the kind of computers that we can realize today. This requires working with an abstract model of computers or computation, and as we will show, this has more to do with nature of problems rather than computers. This is our belief at the moment. What exactly do we mean? We mean by that suppose we cannot solve one particular problem in a computer, it is not so much about the limitation of that computer. If we had a bigger computer, we could have solved it. Of course, there are problems which are like that, but we are not interested in that. We are interested in those problems which are inherently unsolvable or inherently only partially solvable. So this has more to do with the nature of problems rather than computers. So we have no other option but to be sort of formal and mathematical in this whole course. Okay. My lecture will not be that, and Dr. Sudeshna Kole after this will take forward this course, and as you will see that it has to do with very formal methods. There is no other option. Okay, now let us come to formal systems. So formal systems is defined this way. First, we define a finite set of symbols known as the alphabet, which concatenate to give formulas. That means so that a formula is just a finite string of symbols taken from the alphabet, and we have a grammar consisting of rules to form formulas. That means given the alphabet, first of all, the alphabet has to be defined. Then we have to talk about the grammar, which gives us the rules to concatenate these symbols in order to get what are known as formulas or well-formed formulas. Okay, formulas which are formed according to the grammar that has been given. If it can be formed using the rules of the formal grammar, it is often required that there be a decision procedure for deciding whether a formula is well formed or not. Given a string, is it a well formed formula? So we should be able to determine that. Then we come to a set of axioms or axiom schemata consisting of well formed formulas. A set of inference rules. A well-formed formula can be inferred from the axioms is known as a theorem of the system. That means we have the axioms, then we have some inference rules. As I was saying, that the difference from an axiomatic system to a formal system is that the inference rules are also specifically mentioned. So, in order to define a formal system, we have to give an alphabet, we have to give a grammar for forming well-formed formulas, we have to give the set of actions, and then we have to give the set of inference rules. Okay? Now, what is the derivation in a formal system? The derivation rules determine in which cases a formal expression A can be deduced from other formal expressions B1, B2 to Bn. If n equal to 0, that means it does not require any prior formula to be proved in order to prove that. That means what? That are given to be true. So I am using the word true. That means that it is valid. So if A is given as a true, then of course it is an axiom. Then A is called an axiom. But then there are other formulas which are not axioms, but which can be derived from an axiom through certain steps. Derivations are either sequences or tree diagrams made of formal expressions according to the derivation rules. Okay. If there are only axioms at the vertices of the derivation tree, which means starting from the axioms and taking the inference rules one by one, whatever it is, we can finally derive the expression A. Okay, then the formal expression at the end of the derivation is said to be deducible or derivable in the formal system. So I think that is okay, that is very clear. Effective formal systems. Very interesting formal systems are those for which the language and the concept of derivation satisfy the requirement of effectiveness. That means we have, essentially algorithms for one thing for determining whether a given expression is a well-formed formula or not, and if it is, then if it is derivable, then we should be able to get that derivation. So this means that there must be an effective procedure for determining whether an arbitrary sequence of symbols is an expression of the formal system or not. The concept of a derivation must satisfy the same requirement. The concept of a deducible expression in effective formal systems is generally speaking not effective. That means what? Well, a particular, you may be, given a deduction, you should be able to see that whether, yes, of course, this is according to the inference rules. But if I sort of generalize it, try to generalize it, that which formula are deducible, which formula are not, this in general, you may not have an algorithm for this. That means they are generally speaking not effective. Okay. We will see examples of that. Okay. Now we come to mathematical logic. Mathematical logic is at the foundation of mathematics. So, since we are doing things in a very formal way, we start from logic. And in mathematical logic, one term is often used called a calculus. What do you mean by a calculus? A calculus in mathematical logic is an effective formal system given by the rules of formation of expressions. That means we should be able to say whether a particular formula is well formed or not, and constructing derivations in that calculus. The expressions of a formal system are regarded as purely formal combination of symbols. And we talk about the two basic calculi, are zeroth order logic, also known as propositional calculus, and first order logic, also known as predicate calculus. And why do we stop there? Why not a second order logic and a third order logic and a fourth order logic and so on? Well, they are there in the sense that as formal systems we have second order, third order, etc. But, well, propositional calculus you must be knowing because you have done Boolean algebra and you have used it in your simple second year class whenever you are designing, say, a combinational circuit, you are giving a Boolean expression, which is an example of something expressed in propositional calculus, as you will see. And then we go to first order logic, but beyond first order, it is difficult to find so-called effective methods. Okay. So that is why we are stopping here. And as a matter of fact, this is where the sort of boundary somewhere is there, where some things we can do and some things we cannot do. Let us proceed. Now, in any mathematical logic, the important properties of logical systems, there are some important properties like consistency. No theorem of the system contradicts another. Okay, this is well, I mean, now let me just put an example in your propositional calculus. It should not be that P is a theorem of the system. You can derive P and you can also derive not P. Then the system is not consistent. Okay, and we sort of insist that it should be consistent. Because if consistency is not there, we really cannot talk much about it. So we always insist on consistency. This is something. We may see the problems in other properties that I will be talking about, but consistency is something that we always insist on. Because if something and its direct contradiction both are provable in the system, then the system is of not much use to us. Next property is validity. The system's rules of proof never allow a false inference from true premises, which means that the rules of inference or rules of proof should be such that whatever we prove in that system, that should be true. That means it is not a false inference. Okay. And we get into some problems here, but this is something we would like to have. Validity is one important property. Another property we like to have, we sometimes have them, we sometimes don't, which is called completeness. If a formula is true, it can be proven. So if a system, formal system is complete, then if a formula is true, then we should be able to prove it. That is, it will be finally be a theorem of the system. And the converse of this, the soundness, which means that if any formula is a theorem of the system, it is true. This is the converse of completeness. Note that in a distinct philosophical use of the term, the soundness, an argument is sound when it is both valid and its premises are true. That means you have derived it following the rules of inference properly, and naturally any proof, I mean, in order to prove something, you have to prove something else. In order to prove that, you have to prove something else. While going that means going down the derivation tree, if you like. Finally, it must end in the axioms. So because that's why we say that the leaves of the derivation tree are going to be axioms. The inference rules, they must be valid, and the premises, the axioms must be true. And the next property is expressivity. How much we can capture in our formal system. Okay. For example, say the propositional calculus, which you have seen, as I said, in simple Boolean logic. That is very nice. It has all good properties. Why can't we stop there? Because it cannot capture many of the systems we like to talk about. So that is why we cannot stop there. Its expressivity is very limited. So the predicate calculus or the first order logic, this includes, sort of propositional calculus in its bowels. In a sense that, okay, propositional calculus in a sense is subsumed by the predicate calculus. And its expressivity is much more. What about a second order logic? The expressivity of a second order logic would be much better than first order logic. But the problem that the reason why we don't go to higher order logics is because
So you got muted again.
Is it all right now?
Yeah.
Yes.
Okay,
Yes.
thank you. Thank you. Okay. Now we come to the concept of semantics, the idea of truth. We had, whatever we had been talking about, hello?
Yeah, we can listen.
Yes, sir, we're going.
Okay, all right, thank you. Okay, so we can, we had talked about the syntax, that means the rules of grammar, which allows you to form those strings of symbols which are well-formed formula. Now we talk about the let me see the semantics. A formula in a formal system is just a finite string of symbols taken from the alphabet without any meaning associated with them. That is the syntax. Semantics is derived by associating a domain of discourse so that the truth values of logical propositions or predicates, domains of non-logical variables, if any, and non-logical functions can be defined over this domain. Such an association is called an interpretation or a model. And if we have some system, let us say the system of natural numbers, okay, can it be an interpretation of certain logic? Then naturally, if we can then define that logic and work with them, then we are actually working with a natural number. That is what we start, where we start from. Okay, as we will see. So, for semantics, you associate a domain of discourse, then give a mapping. Now, you could have associated some other domain. Now, one particular symbol P in the syntax, let us say it stands for a predicate or just a proposition. In one particular interpretation or domain of discourse, P may be true. In another interpretation, P may be false. And there may be formulas which are true in all interpretations. For example, if you say P or not P, that is going to be true in all interpretations. Similarly, if you say P and not P, that is going to be false in all interpretations. So there is a core which are sort of true everywhere. There is a core which are false everywhere, and we are interested in those. And of course, then there will be specific to the domain, some particular proposition or predicate may be true, some particular proposition or predicate may be false. Okay? So this gives us the meaning or the interpretation or the model of the formal system. Okay? And if we can model some particular domain of interest, then that is very interesting to us. For example, can we, as I said, can we model, can we have a formal system where the natural numbers would be a model? Okay, then that would be a first step and very important step for us. We will see whether we can do that or not. Well, just one thing, I'll quickly go over this because you already know this. What is called the zeroth order logic or the propositional calculus. This is a branch of logic. It is also sometimes called zeroth order logic. It deals with the propositions which can be true or false and relations between propositions, okay, including the construction of arguments based on arguments means as we argue things, etc., as we justify things based on them. Compound propositions are found by connecting propositions by logical connectives. Propositions that contain no logical connectives are called atomic propositions. Okay, P, Q. The formal language of propositional logic consists of formulas built up from propositional symbols, that means P, Q, R, S, etc., and logical connectives, and or not. The only non-logical symbols in a formal language of propositional calculus are the propositional symbols, which are often denoted by capital letters. To make the formal language precise, a specific set of propositional symbols must be fixed. Okay. Any combinational circuit, for example, can be expressed in this logic. So that is a part of the expressivity of zeroth order logic. But unfortunately, that is we cannot go much further. Unlike first order logic, propositional logic does not deal with non-logical objects, predicates about them, or quantifiers. We will define all these. You know them, but still we will sort of revise this today. However, all the machinery of propositional logic is included in first order logic and higher order logics. In this sense, propositional logic is the foundation of first order logic and higher order logic. That means propositional zeroth order logic is embedded in all of them. Okay. So first order logic will contain whatever is there in the propositional logic and will have something more. And what would be an interpretation for propositional logic? The standard kind of interpretation in this setting is a function that maps each propositional symbol to one of the truth values, true or false. And this function is known as a truth assignment or valuation function. In many presentations, it is literally a truth value that is assigned. P is true, Q is false, and so on. For a language with n distinct propositional variables, there are 2 to the power n distinct possible interpretations. Each P, Q, R, etc. can be given either the value either true or false. So many interpretations are possible, which are essentially the essential part of the interpretation. Then a particular interpretation or model can have other things which are not really relevant to this formal system. That may be there. Given any truth assignment for a set of propositional symbols, there is a unique extension to an interpretation for all the propositional formulas built up from those variables. Okay. Okay, if you say that P is true, Q is false, P or Q will be true, and so on. This extended interpretation is defined inductively using the truth table definition of logical connectives discussed above. Okay? So if it is, let us say, and A and B, both A and B must be individually true in order for A and B to be true. That kind of inductive definitions. Okay? Using the truth tables. You know all this, there is no problem at all. Let us now come to first order logic. Acha. Just a minute, I will just take leave from you for a couple. Hello, I am back. I hope you can hear me. Some of you can unmute and tell me. Can you hear me?
Yes,
Yes,
sir.
sir.
Yeah.
Thank you very much. Thank you very much. Okay. Actually, I am very sorry. I had started with a set of slides which are an older version. So I just changed the version. This is the version. You have the new version, so there is no problem. Okay. All right. I was here, I think. So, okay, we have talked about, and now we start first order logic. First order logic, also known as predicate logic or quantificational logic or first order predicate calculus, is a collection of formal systems used in mathematics, philosophy, linguistics, computer science, everywhere. Actually, first order systems are used almost everywhere. I mean, in many, many places, almost all places. First order logic uses quantified variables over non-logical objects and allows the use of sentences that contains variables as well as functions, so that rather than propositions such as Socrates is a man, one can have expressions in the form there exists an X such that X is Socrates and X is man. Where there exists is a quantifier, while X is a variable. This distinguishes it from propositional logic, which does not use quantifiers or relations in this sense. Propositional logic is the foundation of first order logic. We have talked about it. Okay. A theory about a topic is usually a first order logic, as I told you that this is because as you go higher, the expressivity would be more higher, but you will not have effective methods. So we use first order logic in all places, together with a specified domain of discourse over which the quantified variables range. Now, if you say for all x, where x is a variable, the domain of x would be this domain of discourse. Okay. Finitely many functions from that domain to itself, finitely many predicates defined on that domain, and a set of axioms believed to hold about them. Sometimes theory is understood in a more formal sense, which is just a set of sentences in first order logic. Okay, so first order logic is the standard for the formalization of mathematics into axioms and is studied in the foundation of mathematics, Peano arithmetic, Zermelo-Fraenkel set theory. I mention these two because arithmetic and set theory, I mean, you're talking about the foundation logic, and then what is built up on that foundation. One important side is arithmetic, another important side is set theory. So this Peano arithmetic and Zermelo-Fraenkel set theory, they can be modeled using first order logic. Are axiomatizations of number theory and set theory, respectively, into first order logic. No first order theory, unfortunately, these are some hard facts we are going to encounter now. One is that no first order theory, however, has the strength to uniquely describe what is called a structure, and we are not going into the details of structures in this course, with an infinite domain, such as the natural numbers or the real line. Axiom systems that do fully describe these two structures, that is categorical axiom systems, can be obtained in stronger logic such as second order logic, but we are not going to go into this. So what we will see is that what can we do using first order logic. Let us say we cannot leave natural numbers because that is the basis of much of computation that we do, but we are sort of proceeding with the understanding that this will not capture everything about first order logic. But we have to sort of follow this because we have this overwhelming requirement that it has to be effective. That means there has to be an algorithm which can run on a computer, on a physically realizable computer. So this is absolutely overwhelming requirement. So we sort of keep on with first order logic. So the boundary of what we can compute, that is what we were talking about, that what we can compute, what we cannot compute, what we compute only partially, is somewhat hazily discernible in the infinite domain of all theories that can be captured by first order logic. So can it capture arithmetic? Can it capture set theory? At least up to, we know that an infinite set, in a sense, where that real infinite set we will not be able to handle, but at least up to arbitrarily large cardinality, the answer is yes. Decision problems, some of them. We will go into in the course, we will go into the details of what kind of decision problems we can solve and what kind of decision problems we cannot solve. Functions on natural numbers, once again, some of them. So we will define which class of functions on natural numbers we can actually compute. So we will now discuss first order logic and arithmetic in greater detail. By greater detail, and actually this detail is going to be, I think that many of you know this, understand this, so this part, the next part is going to be a little boring for you, because this is all very simple, but we are refreshing that here, because this is going to be used all the time. This is a language, first order logic, that is a language that will be used in many, many places. Okay? So we will go through this quickly. We will go through this and see not only the first order logic, how can we do something. Let us take arithmetic, for example, is very intimately connected with computers and computation. How can we axiomatize it, meaning express it in first order logic, and whether that is enough or not. Okay? All right. So first let us talk about the language of first order logic. The basic components of first order logic are called terms. Essentially, a term is an object that denotes some object other than true or false. The simplest kind of term is a constant. A value such as 8 is a constant. The denotation of this term is the number 8. Maybe. Possibly that is the kind of denotation that you would like to have. That is the kind of semantics that you would like to have. That this symbol 8 would actually stand for the number 8 as we know them. A value that is contained in the sets n, that is the natural numbers, and z, the positive natural numbers. We often use constants in maths. We introduce them by writing things like, let S be the set, let us say 1, 2, 3. So the set of numerals 1, 2, 3, that is the set S. In this case, we have introduced a constant
Sir, you muted again.
Is it all right now? Is it all
Yes.
right now? Yeah, okay. So, I'm not doing anything somewhere. So it seems that users have a lot of freedom here to mute and unmute others. Anyway, so thank you. We will live with this, no problem, because we will have to take classes in this mode all the time, most probably throughout the semester. So we will get used to it. Thank
Sir, I
you.
believe
Yeah.
you can set some settings when you create the meeting where you can choose who has the control to mute you. Like as the organizer, you can be the only one in control.
Okay, I will have to appeal to Dr. Sudeshna Kole. Okay, I am so old, I cannot do all this, so I'll request her to do it in the next class. Okay.
Yes, sir, if
For
you need, we can send you step-by-step instructions or
I'll tell her, she knows, she will be able to do it. Okay,
Okay.
from the next class it will be all right. Okay. Okay. Can it be? No, what they are saying is that it is possible for you to set up things in such a way so that other people cannot unmute you. Maybe that is possible. So she will do it from the next class. So today we will proceed. Okay. All right. Okay. So we can have constants that stand for any kind of object. For example, we could have a constant that stood for or denoted the individual somebody, Michael Ulrich.
Sir, you're muted again.
Sir, you're muted again. Who is doing this?
This is too much. I do not know. Can it be very simply done? I am talking to Dr. Pole. Okay, just give me 5 minutes. Let us see if she can do something. I cannot. Okay, I hope you can hear me.
Yes, sir.
Yeah, thank you. We have done something. I hope that works. I mean, if it does not, sorry. Anyway, so we were talking about language of first order logic, and we have talked about terms, and we have talked about constants, which are terms. Okay. There are other terms. We will talk about it. I've introduced a. All right. So that's it. Now, the second simplest kind of term is a variable. A constant is a term. A variable by itself is a term. A variable can stand for anything in a set of objects. That is, a variable of type n could stand for any of the natural numbers. Let's just formalize this before going any further. A constant of type t is a name that denotes some particular object in the set T. A variable of type t is a name that can denote any value in the set T. By the way, there are typed systems and untyped systems. In a typed system, there can be multiple types. So we sort of say, like you have integers, real numbers, etc. Similarly, uh, so a constant can be of type t or a variable can be of type t. But in quite a lot of this, when we have, use this first order logic, we have an untyped system. In that case, we will simply not mention t, as you will see. Okay. We can now introduce a more complex class of terms, namely functions. In FOL, we have a set of function symbols. Each symbol corresponds to a particular function. It denotes some function. Each function symbol is associated with a natural number called its arity. Okay, it's a function of 2 variables, 3 variables, 1 variable, 0 variable, whatever. This is just the number of arguments it takes. Each function symbol has a return type associated with it. So formally, let f be an arbitrary function symbol of type t with arity small n, which is a member of which is a natural number, taking arguments of the type t1, t2 to tn respectively. Also let 1 up to n be terms of the type t1 to tn respectively, so that these can be the arguments of f. So we can write f1 up to n. So these are all arguments of type t1 to tn is a functional term. I mean, the way we would expect a function to be formed, the function symbol followed by a parenthesis, followed by a list of arguments, then the closing parenthesis, okay? That is the way we use it, and each of these, there may be multiple types of sets, multiple types, and each of 1 to n, arguments 1 to n, would be of types t1 to tn. So this is how we write it. So this f1 to n, etc., this is a term. Okay? Consider the function plus 2, 3 is an acceptable functional term. Plus 0, 1 is acceptable. Plus 1, 2, 4 is acceptable, because plus 1, 2 has a return type integer, and so plus of that integer and 4, so this is acceptable. Plus 0, 1, 2, 4 is acceptable. But plus minus 1, 0 is, why is it? Is it not? Because there is a negative number there, that is not defined. Okay? The language of FOL contains a stock of predicate symbols. So we have talked about constants, we have talked about variables, we have talked about functions, ordinary functions, and then now we are talking about predicates. These symbols stand for relationship between objects. Definition: let P be a predicate symbol of arity n, small n, in natural numbers, which takes arguments of types t1 to tn. Then if 1 to n are terms of type t1 to tn, as we were talking in the case of ordinary functions, I mean, as you will see, the predicates also written like ordinary functions. Only thing is that they are relations, so they are either true or false. Anyway, of type t1 to tn respectively, then p1 to n is a predicate which will either be true or false under some interpretation. Okay? So predicates. So we have now introduced predicates. So a predicate just expresses a relationship between some values. What happens if a predicate contains variables? Can we tell if it is true or false? Not usually. We need to know an interpretation for the variables. For example, px. Let us think of the something predicate. Let me give you two predicates. One is even, the other is odd. And we can say even 2 is true, even 64 is true, even 23 is false, and so on. Now, not usually. So, but if I say even x, you are not sure. It depends on the value of x. So, not usually. We need to know an interpretation for the variables. A predicate that contains no variables is naturally a proposition which we are all familiar with. So, predicate of arity 1 are called properties. Man X, mortal X, malfunctioning X. Example, the following are, these are properties. So, man is a property of X. X may be a man, X may be a tree, whatever. In that case, a man will be, say, man, myself. True, man, a tree. False, and so on. Predicates that have arity 0, that is, take no arguments, are called primitive propositions. Predicate may be combined using the logical operators not, and, or. Okay? Language of first order logic. We now come to the central part of this first order logic, which is quantification. Consider trying to represent the following. All men have a mother. Every natural number has a prime factor, something like that. We want to express. We can't represent these using the apparatus we have got so far, so we need quantifiers. In Z, we shall use two quantifiers. For all, I mean, that is the symbol, and the universal it is called the universal quantifier, and it is read as for all. Then there exists, it is like this thing of E, capital E, a mirror reflection of capital E. The existence of quantifiers is read there exist. I mean, most probably you know all this, but anyway, let me, since this is, we are doing it formally, so I am just repeating this. The simplest form of quantified formula in Z is as follows. Quantifier signature predicate, where quantifier is one of for all or there exists. Signature is the form of variable colon type, and predicate, of course, is a predicate. Example, for all X of type man, mortal X. Okay? That means every individual who is a man will be mortal. For all X of type man, X is mortal. That is, all men are mortal. So we have expressed that. If the logic is used in a type-free manner, we will drop that type. For example, for all X mortal X, we can say. That X is of type man. Naturally, you cannot do that if you have multiple types. So you cannot do that. But quite often, we do not have multiple types. So this is good enough. Okay. Note that the universal quantification is similar to conjunction. We say for all n in the, which is in the set 2, 4, 6, even n. Actually, we are saying even 2 and even 4 and even 6. Is the same as even 2 and even 4 and even 6. In the same way, existential quantifier is the same as disjunction. There exists an n, 7, 8, 9, prime n is the same as prime 7 or prime 8 or prime 9. Okay? So that is about quantification. Just one other thing, how to handle negations. Universal and existential quantifiers are in fact duals of each other. Just as you know that and or are duals of each other, okay? When you say negate an and, you may be converted to an or, okay, and vice versa. Similarly, for all X of type T, Px is the same as not there exists X of type T, not Px. Think about it, that if for all, that means there is no x for which not px is true, which is the same as for all x, px is true. Saying that everything has some property is the same as saying that there is nothing that does not have that property. And its dual, there exists an x of type t, px, is the same as not for all x, t of type t, not px. Saying that there is something that has the property is the same as saying that it is not the case that everything doesn't have that property. All right? This is important because if you want to take in negations inside some parentheses, naturally you, just as you do for and or, you change the ands to ors, and ors to ands, and the individual terms you simply not them. Similarly, there exists, you change them to not for all, and for all, that means not for all you replace with there exists, and not there exists you replace with for all. And then, of course, so this is about the language of first order logic. Interpretation of first order logic, there are an infinite number of interpretations of first order logic. We will talk about some of them. An interpretation of a first order language assigns a denotation to each non-logical symbol in that language. It also determines a domain of discourse that specifies the range of the quantifiers. When I say for all x, the x of type such and such, that type such and such becomes very specific when you fix up the domain of discourse. The result is that each term is assigned an object that it represents, each predicate is assigned a property of objects, and each sentence is assigned a truth value. In this way, an interpretation provides semantic meaning to the terms, the predicates, and the formula of the language. Okay. So we have talked about the language of first order logic, and we have seen that what an interpretation of first order logic means. After this, we will go into a specific interpretation, meaning we are going into a specific domain, namely natural numbers. Because remember, our goal that we want to find out about computation. And the first thing about computation you think is what you can do with a simple calculator. You can do add two numbers, subtract two numbers, multiply, divide, etc., etc. The question is, can we capture these in first order logic? But before we can do that, before we can capture arithmetic, we have to capture the natural numbers themselves. Okay? So we will get into that part now. So they are called Peano's axioms. Essentially, it is capturing the natural numbers. After you have captured the natural numbers here, let us say we start from with 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. up to an arbitrarily large number. We are not claiming all numbers, all natural, all about this thing, but up to an arbitrarily large natural numbers, whether we can capture that. And for that we have a set of axioms. We note that we are doing this formally. So we have to do this in a rather painful manner, in the sense that giving all the details. You cannot jump any step saying, this is obvious. Okay. Actually, by coming to formal systems, we are trying to get away from this style of reasoning, that this is obvious. Okay. Nothing is obvious. So we will do everything formally. As a matter of fact, there was Pino's axiom, I'll just get ahead of myself a little and tell you that when Pino's axioms were proposed and found that, okay, this can model the natural number, and there was a great, this thing by Hilbert, famous mathematician, who wanted the whole of mathematics should be such that there is nothing is left to imagination or your leap of faith or your obviousness, etc., etc. Everything will be done formally. And there was this thing by Bourbaki group of people who started that they tried to do everything in a very formal manner. It went up to quite a lot, went forward. That means proving all of getting all of mathematics into strictly formal systems, and then it was sort of, it petered out, and there is a reason why it petered out. I'll come to that later on. Anyway, coming back, let us come to Pino's axioms. So this is the axiomatic approach to mathematics. In order to approach arithmetic in a formal way, we have to be very careful when proving our various propositions and theorems to only use results we know to be true. Okay. When you prove this, naturally this becomes a result which you know to be true, so that in later proofs you can use this particular one. Okay. But for this particular one, you are allowed to use only those things which you know to be true. All right. So this is what makes things a bit painful, in the sense that the very obvious things we will go to great lengths to prove them. However, many of the statements that we take to be true had to be proven at some point. Those proofs, of course, relied on other true statements. If we continue to trace back our mathematics proofs, we begin to notice that mathematics must have some initial set of true statements that cannot be proven. So these are the axioms. These statements, known as axioms, are the starting point for any mathematical theory. In this section, we will axiomatically define the natural numbers n. As we move through the various axioms, we will see that each one is crucial in defining n. You cannot drop any of them. That means that is a sort of a minimal set. If you drop any of them, you will get stuck. So in such a way that they are equal to the set of natural numbers, and as I said, that we will take the set to be starting from 0. So 0, 1, 2, 3, etc., which are the natural numbers that we know and love. After establishing this, we will establish the basic arithmetic properties of operations on n, defining additions and multiplication. So this is our target today. Now please note that I have written the set opening brace 0, 1, 2, 3, Where did I get this? Well, actually I have jumped ahead. For the first set of 9 axioms are just to prove that yes, indeed we can define a set like this. When I write 0, 1, 2, 3, ... all of you understand what it means. Okay. But you do not understand this formally. You have not proven this. You have not proven that such a set may indeed exist as an interpretation of certain first order systems, which contains, apart from the basic logical truth value inference rules, etc., certain axioms known as Pino's axioms. That is what we will be doing first. So axiomatizing the natural numbers, in this section we will develop the Pino's axioms and use them to provide a completely formal definition of the natural numbers n. In what follows, it's best to train yourself to assume nothing, and use only statements that are known to be true when axioms or statements Or it may be definitions. Okay, when I give the symbol 2, this is defined as something. So we have to define that earlier. Sometimes, and statements that from that we can get from these actions. Okay, we will formalize the notion of equality. First, we have to formalize the notion of equality, because that is something that we will be using all the time. This, etc. in our derivation itself. So, and then present the Pino's axiom. The notion of equality, when approaching mathematics axiomatically, it is important to note, not assume anything at all, including something as rudimentary as how equality behaves. After all, equal to is merely a symbol. Remember that in a formal system, first you have only symbols, until we declare it to have some important properties. Below, we will define the natural numbers n axiomatically. So before we get into that, let us establish the properties that equal to should have. First, every natural number should be equal to itself. So this is known as the reflexive property. So for every x in n, mind you, we have not properly this thing to come to n as such, but let us, for the time being, let us ignore that. For every x in n, x equal to x. So that is the reflexive property. And then we have the transitive property next. If one natural number equals to a second one, and then that second one should equal to the first one, this is the, sorry, not transitivity, symmetry. First one is, this is called the symmetric axiom. That means for all x, y in n, if x equal to y, then y equal to x. It has to be symmetric. And then transitive. The next property allows us to say that if one natural number is equal to a second, and that second natural number is equal to third, then the first and the third are equal to each other. This is known as the transitivity axiom. That is the axiom 3. For all x, y, z in n, if x equal to y and y equal to z, then x equal to z. This is, you know, the equivalence relation. The above three properties of reflexivity, symmetry, and transitivity come up numerous times in essentially every mathematical field. Equality is an example of what is called a relation. And relations that enjoy the above three properties are known as equivalence relations. By the way, you can have many formal systems where equality is not there at all. All right. Anyway, for us, our purpose, we will, we have defined equality and we will go with this, because we will require this in arithmetic all the time. So there remains one last axiom related to equality. In each of the above axioms, whenever we used a symbol like x, y, or z, we always had an assumption that these elements were in the natural numbers. If we don't make that assumption, then we may run into problems. To help get around this, the fourth axiom, called the closure of equality axiom, says that if you have a natural number that is equal to something, then that something also has to be a natural number. Axiom 4. For all x and y, if x is in n and x equal to y, then y is in n. So that is the closure property. You cannot have a natural number which is equal to something else which is not a natural number. All right. This is important. And unless you have this closure, whatever we were doing previously, that means x in n, y in n, etc., we were talking, we cannot do that. In other words, the only way for something to be equal to a natural number is for it to be a natural number itself. In different versions of the Pino's axiom, the above four axioms are excluded, as they, and that means these properties of equality are frequently assumed to be true as part of the logic. But for some completeness, we have mentioned them, though we include them in these notes. Furthermore, their inclusion here highlights the importance of questioning even the most basic mathematical assumptions. Please note, why do we have to be so formal? Why at all? Remember, say later on when you do arithmetic, you will do it in an ALU through computers, through some electron flow or moving of holes or whatever you do. All right. So, does it have the arithmetic properties? Well, if we define arithmetic formally and in this logical fashion from the beginning, and show that whatever we mean in arithmetic, so this is a direct mapping of that, etc., then we can say indeed we can do arithmetic inside a computer. Okay? All right. Now proceeding with further actions. Now we are ready to present the main Peano axioms. It is important to keep in mind that when Peano and others constructed these axioms, their goal was to provide the fewest axioms that would generate the natural numbers that everyone was familiar with. The insight is that this could be done by asserting the existence of at least one natural number, and we'll take it as 0, and then defining a function called successor function that can be used to construct the remaining natural numbers. An obvious element to axiomatically include is the natural number 0. That means the next axiom will state that 0 is a natural number as an axiom. Axiom 5, 0 is a natural number. That is, 0 is in n. In alternate versions of Peano's axioms, 5 actually replaces 0 with 1, as I said. That is, it starts with 1 or starts with 0. This creates an almost identical set of natural numbers which correspond to positive whole numbers, as we know them now. Whether a mathematician includes 0 in the natural numbers or not depends on the context. We use the convention of including 0 as a natural number. At this point, we are only guaranteed the existence of a single natural number 0. Okay. Is there anything else? Etc. From the axioms, we cannot find anything else as yet. But we will. The next axiom, the successor function I was talking about, the next axiom uses the successor function to generate other natural numbers. As its name implies, the successor function is a function S that has as its domain n, and its range is also n. The next axiom simply states that the codomain of S is also n. Axiom 6. If x is in n, then Sx is in n. What does it imply? We have already said 0 is in n. So S0 would be in n, and then SS0 would be in n, then SSS0 would be in n, and so on and so forth, ad infinitum. So basically, essentially with S, now we have expanded our natural numbers from the set 0 to all 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. That is, if x is a natural number, then so is its successor. As above axiom implies, we will commonly refer to Sx as the successor of x. Intuitively, we should think of Sx as x plus 1. But this is just your intuition. You cannot use this as a proof because right now we have not defined what is plus. Of course, we cannot formally define it this way yet, since we do not know what plus means. At this point, we are still quite far away from having the natural numbers. Why? We have got 0, 1, 2, 3, 4, 5, etc., everything. So what is left? Well, you have not really shown that apart from 0, 1, 2, 3, 4, 5, whatever, and so on, it does not contain other things. It does not contain mango and jackfruit. That is, so this is formal, remember? So formal, for example, if we have n equal to 0 and define s0 equal to 0, then all of them, and also note this. For example, if we have, say, n equal to 0, and then define s0 equal to 0, then all the above axioms are satisfied. We, of course, want to avoid this. All right. If I say s0 equal to 0, then you will never get out of 0. So we need another axiom for that. A way to ensure this is to insist that 0 is not the successor of any natural number, including itself, of course. So axiom 7 is, for every natural number x in n, Sx equal to 0 is false. That means 0 is not the successor of anybody. We are saying that for every natural number x in n, Sx equal to 0 is false, meaning 0 is not the successor of anybody. Rephrasing this, using our knowledge of functions, we can say that the preimage of 0 under S is the in the natural numbers is the empty set. At this point, we are slightly closer to having n look more like natural numbers because 0 is there. Then, since there is S0, we know, in particular, we know that S0 is not equal to 0. And thus, it must equal something else. So, some other natural number, we can denote this natural number by 1. Thus, we can at this point, we know that n contains at least two natural numbers, 0 and 1. And then it will come to, if we are to stop here, though, we could not be guaranteed that all the rest of the natural numbers as we know them exist. For example, we could define n equal to 0, 1, where s0 equal to 1 and s1 equal to 1. Again, using our knowledge of functions, we recognize that the fact that s0 equal to 1 and s1 equal to 1 means that s is not an injective function. We have to make it injective. We would like this successor function to be injective. So we have the following axioms. Axiom 8. For all x, y in n, if sx equal to sy, then x equal to y. All right? That means if the successors are the same, then it must have been the same number. Sx equal to sy, then x equal to y. Or in other words, two different elements of the set n cannot have the same successor. If they have the same successor, that means they are the same element. The above axiom has some very important ramifications. First, it excludes the possibility of defining n to be just 0, 1. To see why, notice that we already have S0 equal to 1. So now you cannot have S1 equal to 1. And by injectivity, we cannot have S1 equal to 1. So axiom 6 excludes the possibility of S1 equal to 0. Thus, S1 must be some other natural number which we denote as 2. Thus, we can define 2 is equal to S1 is equal to S0. The similar argument gives us gives that S2 cannot be 0, 1 or 2, so it must be something else 3. Continuing in this pattern, we see that n must contain all the natural numbers that we know. At this point, we have established that 2 equal to S1 and so on. Thus, we formally have that n must include 0, S0, SS0, SSS0, and so on. So is that all? Of course, to avoid so many nested applications of S, we use the numerals 1, 2, 3 to denote S0, SS0 and so on. We are, however, not done. These first 8 axioms have pushed our formal definition of n to include all of the usual natural numbers that we know and love. That is, we know now that 0, 1, 2, etc. is a subset of n. We have not proved its equality. We have proved that 0, 1, 2, they must be there. So 0, 1, 2, etc. is a subset of n. However, what disallows our axiomatic n from containing more? So far, nothing does. To see this, let us consider this version of n that satisfies all the above axioms, but is not the usual natural numbers. We know that is n equal to 0, 1, 2, 3, etc. union A, the set A, comma B. That is, this version of n contains all the natural numbers and also 2 other symbols A and B. We also need to describe the successor functions. On the portion 0, 1, 2, 3, etc., we define S in the usual manner. When S0 equal to 1, S1 equal to 2, S2 equal to 3, and so on. On the portion AB, we can define SA equal to B and SB equal to A. This version of n with this successor function satisfies all the axioms, but is larger than what we would like, than we want on our natural numbers to be. So the next and final axiom will exclude versions of n that are too large from occurring. Before we begin, we need a definition that is inspired by induction. A set V is called inductive if the following 2 conditions are satisfied. 0 is in V, sorry, this is, just a minute. Okay. What happened? Oh, acha. X for X is in V, then Sx is in V. If X is in V, then Sx, this thing is also in V. So that is an inductive set. And the why it is called inductive, obviously it has to do with induction. Of course, the name comes from the fact that the first condition is similar to our base case from induction, and the second condition is analogous to the induction step. The last axiom is many times called the axiom of induction, which says that if V is an inductive set, then V contains the set of natural numbers. Okay. So if V is an inductive set, then V contains the set of natural numbers. That means V is a superset of n. If V is an inductive set, then n is a subset of V. As stated above, the first 8 axioms ensure that 0, 1, 2, 3, etc. is a subset of n. Furthermore, notice that the set 0, 1, 2, 3, etc. is an inductive set, almost by definition. Thus, by axiom 9, it must be true that n is a subset of 0, 1, 2, 3. Thus, finally, we have n equal to 0, 1, 2, 3, etc. Finally, we have defined this set of natural numbers using 9 axioms. Okay, but we have done this formally, we have done this successfully, so we are very satisfied about it. Now let us come to arithmetic. Now this should not be difficult at all, this should be easy. As we know, the importance of n does not stem from its set theoretic properties. Rather, n is of crucial importance because of the arithmetic that we can perform on it. Specifically, addition and multiplication touch every single aspect of our academic and non-academic lives. Given that so much care was taken to axiomatically define the set of natural numbers, we should be sure to carefully define what is meant by addition and multiplication. The Peano's axioms and the successor function allow us to do precisely that. Addition. We will now, using only the information provided in the Peano's axiom, define the operation plus of addition. In what follows, we let A, B be in n. Axiom 5 guarantees that 0 is in n. So we begin by defining what it means to add 0. Excuse me. Thus, we define a plus 0 equal to a. This is by definition. Excuse me. I'm sorry. Okay. To define the sum of any two natural numbers, we use the following recursive definition, which is a plus sb is the same as sa plus b. Now please note that if a, b are also in n, then a, b would either be 0 or it would be the successor of something. So if it is successor of something, we take the s out. If it is 0, the rest of it is automatically included. Therefore, we want to compute, say, let us say 1 plus 1. We note that 1 equal to s0 and get 1 plus 1 equal to 1 plus s0. Then, using a plus sb, this one, a plus sb, we get 1 plus s0 is s1 plus 0. And what is 1 plus 0? 1 plus 0 is 1. So s of 1, which is 2. We can proceed further to compute 1 plus 2 and so on. To do so, we note that 2 is s1 and we therefore etc. 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 Notice that this latter computation relied on the previous computation of 1 plus 1 equal to 2. And the fact that we defined 3 to be s2. Similarly, the first computation of 1 plus 1 relied on using the given fact that 1 plus 0 equal to 1. Iterating this process enough number of times, we generate the usual addition that we use. We have done addition. What about multiplication? Multiplication. When we first learned multiplication in early grade school, it was taught by asking us to perform addition in an iterative manner. Similarly, we can define multiplication as repeated addition. Similarly, the axiomatic multiplication is built upon the previously defined axiomatic addition. As with addition, axiomatic multiplication is given recursively as a dot 0 is equal to 0 and a dot sb is equal to a plus a dot b. So, and now you can sort of do this. So thus we can easily show that a dot 1 equal to a by noting that 1 is equal to s0. So if 1 equal to s0, so a dot 1, so you put it here, a dot sb is equal to a plus sb. So it would be 1 plus, and therefore 1 is equal to a dot s0 equal to a plus a dot 0 is equal to a plus 0 equal to a. We can use this to multiply 3 into 2. Of course, we know that 2 is S1 and so on. And therefore, 3 dot 2 is equal to 3 dot S1 is equal to 3 plus 3 dot 1. And that 3 plus 3 equal to 6. This latter statement, of course, can be shown using enough iteration of addition. All right. So we can see that multiplication is also possible. So we are capturing in the formal system of first order logic the entire natural numbers and arithmetic. Of course, these are not, these are effective methods, certainly. They are shown to be effective, but they are not, efficient. So making the arithmetic efficient is a different ball game altogether. And we will talk about efficiency, etc. later on. But right now, we simply show that it is possible to capture arithmetic in a formal system. I think I will stop here today. Our next class will be on Thursday. So Thursday, we will start from here and just give a overall view of what the rest of the course will contain. This was just some basics of first order logic and arithmetic. Any questions you want to have? Does any of you want to ask any question up to whatever we have done today? What we will do in the course, etc., that will only be clear. That will only be finished when we take the next class. Only thing we have done today formally are this Peano's axioms. What is for first order system, Peano's axioms, and finally we can do arithmetic using the Peano's axioms. Yes, any question, please? Okay, we will stop here. You think about it. If you have any question, we will certainly address them in the next class, or we will continue with our this thing. By the way, as you know, that this time we will not have mid-semester or end semester. Rather, we would have a process of continuous evaluation. So every week there will be some kind of test or assignment. All right. And also in that case, this is the first module, let us say, if I can call it a module, will be 3 lectures. So we have had 2 lectures today, 1 lecture on Thursday. Then on Monday, we will have a test. All right. And I'll tell you what will be there in the test. It is extremely simple. So there is no problem. Okay. Any other comment? Anybody? Okay, thank you.